liftoff of Atlanta.
Holy cow.
Polymers have revolutionised the way we live our lives, and it is impossible to imagine this modern world we are surrounded with without the existence of polymers. It's hard to believe that these buildings have been around longer than our understanding. There are endless possible polymers, with undoubtedly many more yet to be discovered. We are surrounded every day in their varying uses, from the high-density polystyrene used in my phone, to the polyethylene tetraphthalate used in my water bottle, the nylon in my shirt, or the polyurethane used in these climbing holds here. I haven't even had to move to point out various different polymers in numerous applications, but I've barely scratched the surface of the uses of polymers. One of the most amazing applications of polymers is in the use of aerospace. The space shuttle experiences incredibly high temperatures upon re-entering the Earth's atmosphere. Without any form of thermal insulation, the aluminium space frame would simply disintegrate. Numerous different materials are used in varying places to suit the different temperature requirements across the space shuttle. The highest temperature requirements are suited by reinforced carbon-carbon in the nose cone and the leading edge of the wings, whilst the underside of the space shuttle uses silicon fibre panels. But the top side of the space shuttle, as well as numerous other areas, use flexible insulation blankets. Blankets are made of many layers of polymer films based on either Kapton or Mylar. They are separated by very small, fine scrim cloths which provide an air gap to better increase the insulating properties. These blankets are usually treated with either carbon black pigment to better absorb radiation from the sun, or vapor deposited aluminium, which makes it a nice white coating to reflect the sunlight. They are also frequently coated with a very, very thin layer of indium tin oxide, which dissipates the static electricity which builds upon the spacecraft. Kapton is stable right from absolute zero all the way up to 400 degrees Celsius. For this reason, it's perfect to deal with the intense cold of outer space with the massive, massive high temperatures of re-entry. It is also a perfect example of step growth polymerization.
This is the reaction mechanism for the synthesis of Kapton. The first stage of the reaction is when the lone pair of electrons on this nitrogen here on the 4,4-oxydiphenylamine attacks this carbon indicated by the arrow. This forces the bond to break, opening the ring of the structure, moving the electrons onto this oxygen. This forms this ionic intermediate down here. This intermediate can react at both ends, with the amine group down here and the ether group on this section of the molecule here, like so in the previous step. Subsequent reactions force this polymerization to take place, forming this polymer at the bottom, with this being the repeat unit, which repeats n times across the molecule.
Mylar is technically known as biaxially orientated polyethylene tetraphthalate, so it's not much different from the PET used in my bottle earlier. The only difference is that the polymer chains have been aligned from their previous amorphous state through a process of drawing. Mylar is not only a very good insulator against heat, it is also very good at keeping out radiation, and for that reason it is used in 5 layers of it in NASA's spacesuits. Up there, right up there. Another use of the polymer Kapton is in the innovative area of solar sails. The concept of solar sailing is to use the radiation pressure from the sun as well as the solar wind to transfer momentum to the spacecraft through collisions with the tiny subatomic particles. It was first successfully demonstrated by the spacecraft Icaros, made by JAXA, the Japanese Space Agency. This craft travelled all the way to Venus recently. The sail itself of Icaros is made of Kapton at a gigantic 200 square metres, but its thickness is only a tiny, minute 7.5 micrometers. The lightweight, flexible strength of Kapton makes it ideal for this situation, where it must be flexible enough to be packed up in the hold of the launching craft before deploying. It must be light enough to generate the most acceleration possible from the tiny momentum changes from the subatomic particles, but yet strong enough to maintain shape without any form of damage at such a tiny, tiny thickness. The future of polymers in solar sails is very bright indeed, with NASA and private enterprises in extensive research programs of their own, but the development is still being led by JAXA. Thank you, Japan. Polyisobutylene is a synthetic rubber which is added to the jet fuel used in commercial airliners. It greatly increases the droplet size even when using concentrations as low as 100 parts per million. It does this due to the gigantic size of the molecule, leading to a massive increase in the viscosity of the fuel. By increasing the droplet size, polyisobutylene serves to vastly reduce fuel mist in the case of a crash. This suppresses the likelihood of ignition, serving a very important purpose given that 20% of all deaths in air crashes are due to the subsequent fire. The synthesis of polyisobutylene is a good example of cationic addition polymerization, one of the three types of addition polymerization, the other two being radical and anionic. All three methods contain the three crucial stages: initiation, propagation and termination. For fear of boring you to death, I shall show you just one example, the aforementioned cationic addition polymerization of polyisobutylene.
Initiation begins when the two pi electrons in the carbon-carbon double bond attack the activator, which in this case is boron trifluoride. This forms the ionic intermediate shown here. The next stage is propagation, where the chain length grows. This occurs when further monomer units attack the carbocation, like so. This process can be repeated many times in thousands to create massive chain lengths. Propagation ends with the process of termination, which can happen in one of two ways. Firstly, one of the hydrogen atoms here can break its bond to the carbon, attacking the positive charge here, forming a double bond between the carbons, emitting H+. The alternative to this is the attack of a nucleophile to the carbocation. This forms a completely different product shown here.
Another area is the use of epoxy resins. Whilst not exclusive to the aviation industry, their incredibly high strength and performance relative to other adhesives lend themselves very well in the use of sealing crucial parts together in a plane, such as the windows in the cabin, where they must endure vast forces due to the intense pressure differences between the interior and the exterior of the aircraft. Epoxy resins consist of a so-called compound and an activator. The compound is a monomer or short polymer containing epoxide groups at either end, hence the name epoxy resin, whilst the activator is a polyamine monomer. The epoxy resin hardens when the two react together. This is known as the curing process.
These two molecules are examples of a compound and an activator in epoxy resins. We can see in the compound has epoxy groups at either end of the molecule, whilst the activator has amine groups. For the sake of our sanity, we're going to call this part of the molecule R, whilst we call this part of the other molecule R2. So we exclude the non-reacting parts of the compound. The first step begins with the lone pair of the nitrogen on the activator attacking the carbon on the epoxy group at the end of the compound. This forms this ionic intermediate. Negative charge on this oxygen attacks one of the hydrogens here next to the positively charged nitrogen, which puts the electrons back on the positive charge, stabilizing the charges. This forms this. By undergoing the same reaction on the other hydrogen here, attached to the nitrogen, we can see that we attach compound groups to either side of one end of the activator. And because R2 here includes the other amine group at the other end of the molecule, we can see from down here that one activator can be attacked by 4 different compounds, which forms this complex structure down here. All this leads to a massively cross-linked polymer, and which forms one giant lump of epoxy resin in the whole. And in true Blue Peter style, here's one I made earlier, which shows the massive cross-link network.
There are many more examples of the use of polymers in aerospace, from the rise of polymer complex matrices and replacement for metallic components, to the new M5 fibres newly developed, thought to be the strongest polymers in the entire world. New polymers are being developed daily for every aspect of our lives, and that's why I love polymers.